Went white and I was like, what the heck? Okay, go.
You just tell me when you're ready.
We're ready.
Like a blog on the computer.
Yeah,
Yes.
That's so cool.
How much of you have Mr. Allen and Mr. Allen's house with the iPads? You go to Physics 1, a little app she made.
Yes, no, I didn't make that. Some of them made it. They put my picture on it.
Yeah, well, all I know is
It just bothers me.
They made you into an app?
Yeah.
That's how
All this is a picture.
Are you ready?
Miss Warren's
Okay. Okay, so we have our wavelength, our de Broglie wavelength. Here's my H, which is given to me. I have to look for it at the front of my test booklet. Here's my mass of the electron. I knew that if I look in the front of my booklet. And here's my velocity. I certainly didn't know that because I had to find it, and it took me a few steps to find it, but we did. So now I take these two numbers and multiply them, and I'm going to take this divided by this. My wavelength should be 1.74 times 10 to the negative 10th meters. Yay! Okay, so all of this, really good example of a free response question. It's not an example. Why are you shaking your head? Okay. Okay, let's keep going. Chris, shut up. Okay, we have another experiment, and this is more of a conceptual thing, so you really just need to know the name that's associated with what these two guys did. With our experiment here, this is called the Davison-Garmer experiment. So on your notes on your PowerPoint slides, you'll just like underline this or highlight this, put a star next to it, because that's who these two people, that's what these two people are doing their experiment on. Okay, what they did was, it says electrons can be observed to diffract from crystals whose plane spacing is close to the electron wavelength, just as X-rays do. So what happened here, in the first experiment, they took a single piece of crystal, specifically they used nickel. So they're using a piece of nickel, and they're going to expose a little bit of space here. So let's just assume that this is like our nickel, and they're going to expose some space in here. What happened then, they accelerated these beams of electrons, or they accelerated these beams of X-rays. So they took these X-rays, they accelerated them at this nickel, and what they found was they had all of these electrons just scatter away from it after they had tried to shine this beam at such a certain angle. So they have electrons coming toward nickel, and what would happen is the electrons, or the X-rays, would diffract. So I would see a scattering. I see a scattering here, okay? Electrons down into nickel. These X-rays or electrons come off, and they diffract. That was Davison-Garmer experiment. Say it one more time. Two guys took electrons or X-rays. They would accelerate those two. In this experiment, they used nickel, but they used tons of other different types of materials. So in this case, we're just saying it's nickel. So tons of electrons or tons of X-rays, shot it at some nickel. They found those X-rays or electrons will diffract, which just means that they scatter out into different places. Okay? At this point in time, this experiment from these two people were huge. And the reason was, I don't see just these tiny little particles. I actually see them starting to move like waves on a really tiny scale. So this picture is a really bad representation because it does not show them acting like waves. But this is the picture that's in your book. Okay, so really, on a very tiny, tiny scale, he's saying that they're acting like that. And so this was one of the first experiments to show that electrons actually can exhibit wave-like properties. Okay, so this chapter is really important because we're trying to show that there's a relationship in between electrons or particles acting like electrons and particles can of light can act like particles, but they can also exhibit wave-like properties as well. So our wave-particle duality can show both, from what we've seen so far, from what we know. Okay? So that's why we say this is huge. But this is the Davison-Germer experiment. On this one, I don't think this will ever be like an FRQ question. I think if anything, they're just going to say the Davison-Germer experiment was, and then they're going to give you a list of options, and you're going to want to pick the one where they shot electrons or X-rays at a piece of metal or a crystal, and then they found that the X-rays would diffract. So that's what they're going to look for. That's the only thing that I will ask you as well on your test. Okay? All right, almost done. On this one, I don't think that they're going to talk about Schrodinger's wave equation. That's for Physics C, and you're taking the Physics B test. So Schrodinger wave equation describes just the electron wave and how it can propagate through space and time. In our physics book, they talk a little bit about the wave function and his equation and all that stuff, but it needs calculus to do it. And we're not taking a calculus-based physics test, we're taking an algebra-based physics test, so that's why you're not going to see this on here. The only thing that I want to tell you about Schrodinger, just in case, so we're covering our bases here, okay? The only thing that I want to tell you about Schrodinger is that Schrodinger tried to create a new type of an atomic model. And we did talk about Bohr in chapter 27. And we talked about how Bohr said that electrons will go on energy levels. And they had to be very specific energy levels. So do you remember that ladder where we had n equals 1, and then n equals 2, and then n equals 3, and then n equals 4. So those are the orbits that the electron can jump on. And we can have transitions where it can absorb energy and move from N1 to N2, or it can emit energy and release it by going from N2 to N1. So that was in chapter 27. This is Bohr's model. Schrodinger says electrons don't fall in these perfect little circular orbits. They don't do that. Actually, electrons are going to be more within a certain type of space. And the shape of that space depends on something called atomic orbitals, which I don't think you're going to be tested on. Specifically, let's say that my atomic orbital looks spherical. In this cloud, we call this an electron cloud. Within this electron cloud, my chemistry kids, what's the percentage that we can find an electron in this mess?
90%.
Got it, 90%.
90%.
90%. So I have a 90% chance of finding an electron somewhere within this blue shaded region. And this is Schrodinger's model of the atom. Okay, so he, instead of saying that electrons are going to be on these perfect transition levels, these perfect orbits, I have a really good chance in this shape, Schrodinger is saying this, to find an electron. That means I still may find an electron out here somewhere, but the probability is really small. This is the model of the electron, or of the atom that we use today.